Hello out there in video land. Hope y'all are doing well. It is 10 o'clock by my time, and we are ready to do C311. A couple of notes before I go through the rest of our intro to C#. It looks like Rider and .NET 5 are actually busted on Windows. I spent a stupid amount of time getting my Windows VM working and only to find that out. So sorry about that. I didn't realize that. I'd like to give you two options as far as doing the homework with the current busted version of Rider. So thing number one, you can actually change which .NET framework we target. So in Rider here, if you look at these two lines here, these two lines with the little F# project definition on it, if you right-click on those, and go to Properties, thing number one you can do is if you have installed the other versions of .NET, so I can press this ... here and change the target framework. So if you installed like .NET Core 3.1, you can uncheck 5 and check 3.1. You're not going to hurt anything on my end doing that. And 3.1 will work. So if you do that too, so this was the Homework 1 project, and say OK. And then we're going to do the same thing to the tests project. We'll go to Properties, and you see right there it said restoring. It's installing all the dependencies for 3.1 instead of 5. And so yeah, here it says .NET Core app. If I just press ... you don't want net because that's real .NET, and that works differently than Core. But .NET Core app 3.1 is the long-term release version, and it will work just fine. We're not actually using .NET Core 5.0 features, so all of that will work. After it restores the packages, it'll redetect everything in the project. And you may have to like look at the test file before the unit tests solidify. But we can press play on the test class and it'll run all our tests for us. Oh, I only detected one test. That's a little funny. Probably just because it's still working. So that's one option. And that's a fine option. Like I said, you're not going to hurt anything by targeting .NET Core 3.1. You do need to install it first. Oops, I forgot to turn my light on. Hang on, I can look better. I mean, for some value of better. You're not going to hurt anything with that as long as you have .NET Core 3.1 installed, which you can get from the same place we got 5.0. It'll work fine. The other thing that you can do, so that gets you these tests, this little test UI framework down here in the unit test tab, which is, as I said, just fine. It's kind of nice because you can like click on it, you can see what's wrong, and you can eventually down here click on a line of code and get taken to the line of code that failed, which of course isn't really that interesting, but you can see the tests that failed and that kind of stuff. But if you don't really care about that, the other thing you can do is down here I have a terminal tab, and on Windows this is going to open up a CMD prompt. By default, you can change it to a PowerShell prompt if you like, but it'll open up a prompt that's in the current directory. And from this, you can type in .NET space test, enter, and it'll run the same tests that we would have been running otherwise. Like this does the same thing that unit test UI does. So it builds the project, and it'll run all the tests. It'll be a little bit noisy once it gets there. So there it goes. It says down here, failed, 12 failed, 3 passed, 0 skipped, total 15 tests. And we can scroll up and we can see each one that failed. So we can see here that, for instance, are not equal failed, expected, anything except for no answer got no X answer, and it was in the C complexity function on unit test line 41. So you get all of the same information, you just have to read through it instead. When all of these pass, you're not going to see any red text. You're going to see just a message that says 15 passed, and that's it. So that would be the goal. And the best advice I have for you as you're doing this is scroll to the top of this and fix them from the top down. Don't try to go bottom up because that's the end of the assignment. But you go up here and you say, okay, well, GCD, we expect to get 9 out of that. We got 0. Let's go fix the GCD function, right? We don't fix the test, we fix the function. So when we run GCD 918, we should see a 0, right? So those are 2 options for you to complete this. Now, you can do anything you can do in this little terminal tab. You could also pop open a full copy of like PowerShell or CMD, as long as you change directory into wherever your homework directory is. It's the same thing. There's no difference. So that's one way that you can do that. For today, I'm going to just pick up a scratch here. In fact, it's the one I had before. And we're going to complete the intro to F#, right? So I'm going to take us over to the iPad. So we left off defining variables. Nothing was all that interesting. And I'm sure that if you've even looked at that homework project at all, you're probably aware that you've probably seen the way some of this stuff works. But I have a lot of important things to say that are going to save you time, things that I want you to notice. So first off, we have some data structures in F#. The first one that we have that we need to talk about are tuples. Now, tuples are kind of like structs or classes without property names that don't have methods either. They store data, and they store it by the position of the data, right? So you see here we have some tuples, and so like we can store in Barney the value 3. It gets evaluated first before it gets stored. So whatever 3 times 4 is, so 12, my bad. I'm just doing addition. And Brown. And you see here, we get out this tuple, 3, 12, Brown. Now, importantly, look at the type before that equal sign. I want you to always pay attention to that type before the equal sign. It is vitally important that you do that because it gets very confusing if you don't pay attention to these things. So this is of type int, float, string. It's a tuple of an integer, a float, and a string in that order. In order to be a compatible tuple, you have to have another tuple that is exactly this signature. So in this type, signature star means that we are tupling these things together, right? So here's point 1. It's made up of red and a tuple of 2 integers. So you see down here in the type, we have a string tupled with a tuple of 2 integers. All right? Now, if we want to get values out, for the moment, we're going to do something dirty. We'll get a better way to get values out of tuples later, next time, actually. But the first way that we can get values out is using the FST and SND functions, right? So FST means first, so the first value out of point 1, right, is going to be the string, and we'll get red out. If we ask for the second value of point 1, that gets us the tuple, or this tuple 300, 200. And if we ask for the first of the second, that means we're going to get this 300 out because it's the first of the second thing, right? Now, when you define a tuple, always use parentheses because it avoids confusion. Technically, you can define a tuple without those, and it's a problem. So use parentheses. And it's really this comma that means that we have a tuple, right? So comma means tuple. You need to remember that very carefully because there's a thing that's going to bite us in the butt if we forget that. All right, let's keep going. So trivia about tuples. There's no tuple of 1. You can't get a tuple of a single thing because that's just a parenthesized expression, right? So here we're only just evaluating the value 5. Tuples have to have more than one object or that comma in them. So if we try to ask for the first of a 5 in parenthesis, we're going to get an error out that says, hey, you're an idiot. We would have had to have a tuple for that. Now notice here, the error is trying to tell us exactly what's going on. So it says it was expected to have type A times B. And anytime you see this, this is the backtick right below the tittle key, probably next to your 1 key on your keyboard if you have a normal keyboard unlike mine in front of me. I know that they look like these ticks. They're not. I'll show you that actually in the IDE. This is PowerPoint messing with our head. So over in the IDE here, if I did something like that, so let's do FST of 5. And I'm going to press Alt-Enter. Oh, it's going to get mad at me even. Look at that. They're already showing me the error there. Let's do that one more time just so we can actually see it. And, oh, actually it's not. I really thought it was. My bad. It's not the back tick. It's the regular tick. It's the one that's under your quote. Oops. Look, guys, it's still kind of early in the morning to me. Anyway, you can play with these things. You should play with these things and see them work. So if we do something like FST 5,6, we can send this line to, oh my goodness, I might actually have to not use writer in class because it is a little slow. So we can send that to the interactive and we see we get 5 out, right? And if I were to ask for the SND of 5,6, right? We get 6 out, right? So that's a 6 down here. So as you do these things, just know that types still matter immensely, all right? So whenever we create a tuple, really what we're doing, we're using this syntax where we have parenthesis and a comma somewhere, and that creates the tuple type of whatever values we give. So for instance, if we give it an integer and a boolean, we're creating the type int star bool. And the parentheses totally matter, because if I put the parenthesis in various places, I'm going to get different types out of it, right? So let's go see that in action. So if I did, let's do a couple of things here. We'll do 5 comma true, just to see that one. We'll do 5 comma open parenthesis comma true. We'll do 5,6 in parenthesis true, right? And we can do another one here, I think. And no, I can't. We'll just do these 3. So I'll send those over to the interactive, and we'll look at these types that came out. Look, we got int star bool, we got int star open parenthesis int star bool, so this is an integer tupled with a tuple, and then we have int as a tuple tupled with bool. So these are very different and they're not compatible. If you try to send one of these to a function that expects the other, it ain't going to run, and you're going to have a bad time. All right, so we'll do a couple of these, I think. Probably not all of them, but I leave these kind of for you for reasons. So what are the values? And I would also kind of want you to think about what the types of these expressions are. So like A, the second of the tuple 3, 4. The type of that is going to be whatever the type of 4 is, right? Because that's the second thing. So it's int 4, right? What is the type and value of x, right? So if we look at x, x is this big long tuple. Well, we can see here the first thing in it is an int, so we'll say int star. The second thing is a float. The third thing is a string, right? And the values are going to be 3, 12, sorry, 15. I thought it was the same as the other example. And zig, zag. And I want you to notice a very important thing about what I've done here. I have, and I actually haven't. Now I have followed the types. So I need to make sure that my constant 3 is an integer, and I need to make sure my constant 15.0 is a float, and I need to make sure my constant zigzag is a string by putting quotes around it, right? Does D work? And the answer is yes. Yes, it does. What is the type that comes out of D? And the answer is, I hope you were just saying it to yourself, it's a Boolean, right? And what is its value? It's true. 4, 5 is equal to 4, 5, right? And if you don't believe me, right, you can always run these. Pop over to a scratch in your IDE, type the line of code out. Do not copy it from the slides because, again, the slides will trick you, right? And just send it to the interactive, Alt-Enter. And we can see that it's a bool of value true. So if you're ever curious, if you're ever not sure, pull your IDE up and try it. It's the best thing you can do for yourself. All right. What's wrong with the following? If anything, is there anything wrong with second 3, 4, 5? Well, I think there is actually, because this is a tuple of 3, and I think second expects a tuple of 2 no matter what. We don't have a way to get the third item out of a tuple right now. And I think, yeah, I don't even have to send this to the interactive because it's helpfully underlying it. But yeah, we have to have a tuple of 2 to use second and first. So sorry about that. That's the way it is. Is there anything wrong with F? Yes, right? So F, we have a tuple of an int string on one side and 2 ints on the other. Those are not compatible types, so you cannot check their equality. Of course, the same thing is going to be wrong with G, except for we have a float. Okay, let's keep going. Next up, after tuples are lists, and lists are really going to be our bread and butter in this class. Lists are a little different than tuples. Tuples, we can have differing types. They're heterogeneous. In lists, everything has to be the same type. But lists are very flexible, and they are going to be very useful to us. So we're going to use them a lot. So in a list, we separate each value with semicolons instead of commas. Do not forget that, or it will bite you in the butt. I'll show you why. And they're enclosed in square brackets. That is actually completely necessary. Unlike a tuple where if you forget the parenthesis, it'll still kind of do it. It won't do it with a list. So we can create integer lists. You see here it says when we create a list of integers, it says int list. We can create float lists. We can create bool lists. And notice here, you can have a list of one item. That is not a problem, right? But what you cannot do is mix types. So we can't have a list of a floating point number and a string, for instance. It doesn't work. It has to all be the same thing. And if you read the error message here, we expected it to have type float, but we have type string. It's saying, hey, this value is not a thing that we expected based on this value here. And if you can read those error messages, which I hope you can because they're very easy to read, F# becomes a lot easier. Take your time, read the error messages. Don't feel like you're a bad person because you got an error message or something. Take its advice. That's my best advice to you. Notice this one down here. These are a little fun. This one's very interesting. We have one example of forgetting semicolons and commas, and it's causing us a problem. So this is a valid line of code. We can do this. But notice, we probably actually meant this to be a semicolon, where we would have a list of int tuples, but instead we have a list of tuples of 2 integers tuples, right? So if we read this type, we have a tuple of ints tupled to a tuple of ints in a list. So this list, the length of that list is only 1. So that comma made all the difference in the world, and we didn't have those extra parens around all that stuff, and it caused an issue. That is almost definitely, I didn't intend to do that. I just kind of typed it, and I've kept it because it's a good example. The other one down here, we have a list of lists, and there's no problem with that. It'll just say int list. As long as these 2 lists are the same type, so this one's an int list and that's an int list, we can have a list of int lists. No problem at all. All right? Now, unlike a tuple, we can have an empty list, and it's going to be very important to us. There are a couple of different ways that we can represent that empty list. I'll generally use this way here, which is just empty brackets. But there is a built-in called list.empty, which is just an alias for the empty list. Now, note when we have an empty list, it doesn't know what type is going to be in that list. So we get a generic list. What these little tick A things mean, and tick B and tick C, etc., they mean it's generic. That means we don't know what goes in this list yet, but it's compatible with every other list out there because it doesn't have anything in it. All right? So what we have here, the list type constructor, is those brackets and the semicolons. And it is not a tuple, and do not get tuples and lists confused because they don't work the same, and it'll cause you a lot of problems. Okay, you can also check if a list is empty with the .isEmpty method. I suppose it's a method. And it will give you a bool back whether it's true or false. So the empty list.isEmpty will return true. Some other list that has value .isEmpty returns us false. In general, I use this instead, where I just check and see if the list is equal to the empty list. Both are valid. You might see both in notes. It doesn't really matter all that much. So you can do whatever is more comfortable to you as you're writing code. My guess is you'll probably go with this version over here, just because it's what I use most of the time. All right, we can concatenate lists with @. So 1, 2, 3 @4, 5, 6 gives us one list that is flattened. As long as these 2 lists are of the same type, so both of those in this case are int lists, there's no problem. We'll get an int list back, right? So we can concatenate lists, again, as long as they're compatible. If we try to concatenate something that is not a list, it will error at us. We'll say, hey, that's not a list, you can't do that. If we try to concatenate 2 lists of differing types, it will error at us, right? But as long as we try to concatenate lists that are compatible, so this is a list of an int string tuple, we get an int string list out, and it'll put them together. We don't use concatenation a whole lot, but it does come in handy in a couple of places. But more useful than that is the list builder. I might often call this the cons because it constructs lists. It used to be called the cons operator back in earlier languages. List builder is fine. The colon operator is fine. Whatever you like. But this builds lists. So if I have a list on the right-hand side of the colon here, and on the left-hand side, I have whatever something of the type inside that list. So this is an int list over here. 67 is an int list. As long as I have an int at the left-hand side, that int ends up at the front of the list. So we end up with 5, 6, 7. Right? I can cons onto the empty list. I get a list of 1. We put 5 on the front of the empty list. That's an important structure. We'll see that in a few ways later. And I can cons onto variables. So x here, x is of type int list. We can con 6 onto that, and we'll get a list back. Right? So let's go over here to the IDE and play with that a little bit. So I'll do, let me think a second. 1.0 cons the empty list for the first thing I do. Right? And I get the list 1.0 out. It's of type float list. Right? If I do 1.0 cons the list 2.0, make sure you use semicolons. Come on, where's my 3 button? 3.0. Right? We'll send that to the interactive. Come on. You can do it. And we get the list 1, 2, 3 out. It's a float list. Right? But this is equivalent to the list 1.0 cons, 2.0 cons, 3.0 cons, the empty list. Those are all the same, those are both rather the same thing. Right? I'll do the intermediate one here. 1.0 cons the 2.0 cons the list 3.0. So all 3 of these are equivalent. They're all the same list in the end. And we could check their equality because they are the same. You can see them. Right? So this is a powerful tool. It's a little less interesting right now, but we'll see it used quite a lot later. All right. If you want to get values out of a list, for the moment you can use head and tail. So head is always the first value and tail is always everything else. Right? This gets confusing to people for some reason or another, but head is always the first value, tail is always the rest, which means head is a single value and tail is a list of values, right? So if I have z here, it's an int list and it has 1, 2 inside of it, right? If I ask for z's head, I'm going to get the first value out, and note it is an integer. It is not a list, it is just an integer. So it's just the value 1. If I ask for z's tail, right, I'm going to get everything after 1, which is, in this case, a list of 1 item. It is an int list. It is not an integer, it is an int list. They are not the same thing. And so we get the list 2 out. But this one's tricky. What if I ask the tail of the tail? What is left after 2 is nothing, right? So we actually get an empty list out of that. And that's really important for recursion because we need a stopping condition. And that's what this is generally going to be. So the empty list, there's a secret empty list. Don't tell anybody. There's a secret empty list at the end of every F# list. Right? All right. Hey, iPad, next slide. So let's do some of these. I'm just going to do these in the interactive. I'm not going to mark it up. So I'm going to go over to the IDE. I'm actually just going to type them straight up in the interactive. So I'm just going to make this big and type them so that we don't have to, we don't need them around. So the values of these expressions, we have the list 1, 2 at 3, 4. First off, what's the type of this? We have two int lists being concatenated together, right? So the type of it is going to be one int list. And I expect the value to be 1, 2, 3, 4, right? See another one here. Oh, this one's good. 1 cons, 2 cons, empty list. And I'm going to copy that because I'm going to redo it. So we get the list 1, 2, right? What happens if I ask for the head of that list? First off, what value do I get back? I get back the first element, which is head, which is 1 rather. And the type of that is an integer, right? We get 1. If I ask for the tail instead, the type of that tail is an integer list, and the value is the list 2, right there. If I ask for the tail of the tail, I get the empty list. What if I ask for the head of the tail? I get 2 out. So we can get any element in one of these lists if we want. Let's do the last one here. 1, 3. 1, 3, 4 dot head, cons 2, cons 1, 3, 4 dot tail. Now my first question is this a valid line of code? I'll give you a second, and the answer is, yeah, it is. But what's actually happening here? Well, let's put some parenthesis in. So we see that 1, 3, 4 dot head is one expression here, and that's going to result in the value 1. So we're consing the value 1 to 2, so that's the list 1, 2, cons 2, the tail of 1, 3, 4. So that's one expression. And so this is going to be the list 3, 4, right? So I expect we're going to end up with the list, an integer list, 1, 2, 3, 4. And in fact, we do, right? So you got to take these things one step at a time. Even if they look a little complicated, if you read it one step at a time, you might find it's not as complicated as you think. All right. I'm going to leave the rest of exercise 5 to you because I want to get us through functions, and there are a lot to talk about with functions, right? So defining functions. So the first thing you need to know when we define a function is functions look like this. They have let just like a variable, and they have a name. They have a list of parameters, and they're equal to some expression. This expression evaluates, and it is the return value. Right? So whatever x plus y is the return value of the function add here. Now I want to help you read this line underneath it because it's the important thing. This is the type signature of this function. Arrows indicate that we have a function. So add is a function that takes one integer, it takes another integer, and it returns us an integer. So when we have arrows, that's always meaning we have a function, and in this case we have 2 arguments and we have a return type. Every function has a return type. Every function. So we're generally going to see 1 or more arguments, and the last thing is the return type, right? Now, other important things. Notice there's no comma here. There's no parenthesis here because that would be a tuple. And that would change the signature. So here we have a function first that takes a tuple. So x, and what we have here, we're defining that x has to be of a certain type. So if we put colon and a type after it, that means that x must be of that type. So here we're saying x has to be of type tuple int string. This colon means that we're returning an integer out of the function. So the first of x returns us an integer. We run fst of x, just like we said. Notice the type signature, we take an int string and we return an int. So when we run first of this tuple, we end up with the first value of the tuple. I'm going to do this one in the interactive real quick. So let first of x of int star string colon, I'll put a space in there just so it's a little more clear, fst of x. So that gets us a function, right? And I can run first of 5 comma blah de blah, and I get 5 out. Now I'd like to impress on you that let me redefine this function first of x. We don't actually have to have all of these types. Sorry, fst of x. So if I were to take out the return type here, F# will do its best to infer that type, right? And so we can simplify this even further. We don't even need any of that. We can just say first of x. Now it went generic because it doesn't know what x actually is other than it has to be a tuple if we're taking the first of it. But first will still work. Right? So these types, they exist and sometimes they are necessary. Sometimes F# can't figure out what the type of your function is, but that's not always going to be the case. Oftentimes we'll omit it. We'll usually omit it because it's easier to omit it, right? So here's the actual syntax. Let function name, and we have a list of parameters. They're space separated, and optionally they have colon type. At the end of all the parameters, we can have another type, and we have an expression that we're returning. We're going to see a lot more of function definitions. We're going to find out that this is maybe not the only way to define functions later on. All right. So arrow is the type constructor. Arrow means function in F#. So pay attention to types. Let's go back to the IDE for a second and see. Look, we have this arrow. So A star B, we have a tuple, arrow, and A. So whatever the first value in that tuple is, that's the type that we're returning. So int star string arrow int means we're taking an int string and returning an int. If I write another function, so let double x equal x times 2, right? The type of this function, we're taking an integer and we're returning an integer, so it's going to be int arrow int. And if I press enter, you'll see x is an int, arrow int is the return type, right? If I run square, let sqx equals x times x. This one's a little more complicated because you might think that maybe those could be floats. It's going to default to ints. So unless I say, hey, x is a float, it won't fix that to be floats. So that's one thing to keep in mind. F# assumes numbers are going to be ints by default, but you can clamp it down with that colon to tell it, hey, this parameter is of type float, so then it's going to force everything else. Okay, so as we pass parameters, again, they are space separated. There is a space between them. And when we call the function, the same thing is true. So where you're used to in maybe like Java or C++ or whatever, having parentheses and commas, we don't have those because parenthesis and comma means tuple, and we don't actually necessarily want tuples, right? So quote here takes two integers and divides them, and as long as I give it two integers, it will run. But if I try to run quote with 6 and 2.0, it's going to fail because those aren't the right types for quote. Right? So keep that in mind. We need the right types. If I sound boring because I'm repeating that over and over and over and over and over and over and over again, just know that I'm doing you a favor by reminding you. Does F# support overloading? Good question. No. This is a simple answer. If we were to redefine quote, then we would redefine it and the old version wouldn't exist. So you can write like quote floats, or you could write a different version of the function with a different name. But in general, in F#, it is our assumption that we always actually know what we're trying to do. And that's really the point, is that we're forcing the programmer and anybody using the code to do the right thing always. So they always must know what they're trying to do in order to actually do it. There's no, F# doesn't do any work on your behalf so that you have to know what's going on. All right. So this just is solidifying our parameter and return type information. So like here, I've got a function cons that takes a value and a list and conses that list, that value onto the list. So it puts that value on the front of the list, right? And notice the signature here. We have something of type A. We have a list that is of type A list, right? And we return a type A list, right? Because in order to say A : L, that means A has to be the type inside the list, right? And this thing has to be the same type as the list. So these unknown types, A's, F# does its best to fill those types in. Now it can't always do that, and sometimes we're going to have to do little rigmaroles and just tell it what we're doing. But in general, it does its best to always just detect what type we're trying to do. All right, so let's try some of these. What are the results for the following? So we have FA takes an int, returns x plus 1. So if I call FA with 3, I'm going to get an int back, right? Because we're adding 1 to an int. We're going to add to an int. We have to get an int out. So I think that one is 4. FB, we have type x of A and y of B, and we return x. Okay, so FB of 1, 2, 3, 4, right? Well, we're going to get an int list out, 1, 2, 3. And in FB 3, 4, we're going to get 3 out. And there's no problem with any of that. That's totally valid, because those generics give us the flexibility. So I guess you asked me if it supports overloading. Through generics, you can simulate overloading, but it's not really overloading. Because if we try to do anything with X, for instance, so I want to rewrite FB real quick. I'm going to take us to the IDE. We'll take a small detour here. What if I were to write FB, so let FB x colon take A, y is B equals x. This is the first version. This is what we actually had, right? That's no problem, right? So FB of 3, 4, we get 3 out. But what if I rewrite that? What if I write x times 2? First off, it's going to give me an error because I have done something with x, which means that x has to be an integer, right? If I were to take these types off, in fact, let's start with that, x, y, let's just return x. It gives me the same signature, but if I write x times 2 without those types on it, it knows that x has to be an integer. And now FB is less generic because we actually do something with its value, right? So the generics only go so far. That's why I say there is not overloading. We can simulate it with generics, and we'll see a better way to simulate it later. All right. Let's skip to the last one. I don't know. FE, we take an X, which is an int list, we get the head off, and we add 1. So that means that we're getting a value out of an int list. So we have an int here, and we have an int here. We're adding 2 ints, so we're going to get an int back, which means that we're going to get the first value out of this list, which is 3. We're going to add 1 to it, so we'll get 4. Right? Reading code is just super duper important in this language, but as you do that and you pay attention to types, it is not too difficult. All right, let's see what else we got. Return types. All right, so FA, we have something that takes an integer and adds 1 to it. Well, we can't do anything but add integers to integers and get integers back, so that'll be an int. Right? FB of x tick A and y tick B returns x. Well, we've just been doing that, right? FC, we have a list and we get its tail. Right? The tail is the rest of, so we get the first item off and we get the rest, right? Head is the first, tail is the rest, just everything except for the first, which means this is still an A list, right? FD. This FD takes a tuple of 2 lists, right? So this is a tuple, and it returns a list. So cons means that we're returning a list. So we know this is going to be a tick A list, right? And we already did the last one, that is an int. Actually, this is an error. My bad. X is an int. We can't take x.head. Doesn't work. So that's an error. All right. So let's get to recursion. We're actually almost done with this. This went a lot faster than I expected. Let's talk about recursion a little bit. So if we're doing functional languages, generally speaking, we're going to do a lot of recursion. And the reason for that is recursion saves us from having to assign variables. Instead of assigning a variable, we call a function with a different parameter. And by doing that, we avoid ever having to define new variables because the parameters of a function are, in essence, variables. They're just ephemeral. They only exist for that execution, right? So if you think about a for loop, in order to have a for loop, we have to have a loop invariant. We have to have something that is true, and we have to have something that's changing until that thing isn't true anymore, making that loop terminate, right? So in this case, we have to have I getting reassigned every time we go through this loop until I is not less than 10, right? So we have to have program state here in order to end a loop. And we can't do that if we're trying to avoid assignment. And we are avoiding assignment. So we've already seen the factorial function. So we have recursive factorial of n. We check and see if the base case. So if n is equal to 0, then we return 1. Otherwise, we recur. We call factorial again. But every time we call factorial with a problem size. We're doing something here to get us closer to the base case, right? And I'm sure that's kind of I hope that's kind of the statement that you got in C311 about recursion is we have a base case and we have a recursive case where we're trying to get closer to the base case. We're doing some work. So we're breaking something off of n and doing work with it. So in this case, the work that we're doing is multiplying n times factorial, right? All right. So we're going to do a lot of recursion in F#, although most recursion we do isn't going to be this kind of recursion. It's going to be recursion over lists. We're going to process lists a lot. And that becomes very rote and routine and pretty simple. I think this kind of recursion is actually a little harder because we have to think about it a little bit, right? So Fibonacci. Here we have a, Java or C version of Fibonacci. Let's write the F# version, right? So we have Fibonacci. It takes an integer n. The base case is n is less than or equal to 1. Then we can return it. And the recursive case is that we add fib of n minus 1 and fib of n minus 2. So let's go write that. For this, I am going to use the scratch pad because it makes it easier. If you make an error, you can fix it and send it back down. So we want to let the recursive function fib of n equal. Now, F#, we can, on a new line, press enter and indent, and we can start writing our function. So if n is less than or equal to 1, then we'll return n. Else, we will return fib of n minus 1 plus fib of n minus 2. And that is our Fibonacci function. I'll send it down to the interactive. So now we have our Fibonacci function down here, and we can run fib of 10 and hopefully, not rib of 10, fib of 10. And we'll hopefully see that the result is 55, which I believe is correct. Right? Maybe sometime I'll teach you math darts, which is a game me and my buddies invented to play darts with the Fibonacci numbers. All right. So now we have an interest function, and I'm just going to write this interest function. You can see it in the notes if you like. We have a function interest. Actually, I'll pop us over there real quick. We have a function interest. It returns a double, right? So we have a value that we expect. We have a rate, a principal value, and a year. If year is 0, then we return the principal, so there's one base case. Otherwise, we're returning some complicated formula. And literally, I'm just going to rewrite it in F#, right? I'm going to read this and say, okay, well, let recursive interest. We have a rate, a principal, and a year. And if year is 0, then we return principal. Oop, I need a then. Else, I'm going to return the interest. And here I give the rate down to the next function because we're not changing it. The principal has to change. It's 1.0 plus rate times principal, and the year has to decrease. Strictly speaking, I might not need quite all of those parentheses. Now we do have an error here. We have an error on plus. And the issue is probably that it hasn't figured out what type each of these things are. And so we have to see what's actually working together. So we're adding 1.0 to rate. It looks like rate just needs to be told that it's an integer, or sorry, a float to me. Principal also must be a float if we're going to multiply it. And year can be an int. Now we have an error. I have 2 equal signs, so I want to take one of those equals off. That might fix some of this. I'm not sure what this is about, this underline. It's mad that year. Let's see what the actual error is by sending it to the interactive. Value is not a function and cannot be applied. Actually really unsure why that is at the moment. Maybe just some, like I said, sometimes just, yeah, it looks like just adding this parenthesis right here made that happen, right? But now we have our interest function, so we can run interest. The example was 0.06, 1,000, and for 5 years, and we should get 1338.225578 or something very close to it. And in fact, we do. Right? So when you're converting these, if you're converting a C function over, it's mostly the same. Just, you know, sprinkle in some type identifiers, sprinkle in some parenthesis, and you're going to be a happy person. One of the things we do the most, though, is operations on lists, right? So here's list summation. And I am going to type this one in as well, but I will talk about it first. So in lists, when we're doing a recursive function over a list, what we're doing is the base case is usually something about being either empty or close to empty. So when we're at the end of the list, we'll do something that doesn't affect the output. So in this case, we're summing all the items of the list. If we're at the base case, that is, we have no more items left, well, adding 0 to a sum doesn't hurt it. Otherwise, we add the head to the summation of the tail. So the summation of the tail is going to be all the tail values added up. And eventually we're summing the empty list, which is 0, and that doesn't hurt anything. So let's go try this out. Right? So I'm going to type this function in. X is an int list. And so we say if X is empty, then 0, else we're going to add x.head plus the summation of x.tail, right? And that is or one version of summation. Okay, send to interactive, please. Come on. This pausing that's happening here, it's actually just because my computer is super busy encoding the video at the same time. It's not usually this slow. So if we summation, I think I typed that correctly, the list 1, 2, 3, 4, 5, we would expect 15 to come out of this, and indeed it does. If I ask for the summation of the empty list, look, I get 0 because that's the base case. So the summation of 5 should be 5 because it's 5 plus 0. The summation of 4, 5 should be 9. And, we can just build this up as we go. 3, 4, 5. Let's start using cons instead. So 2, 3, 4. Oops. Let me maybe do this. Oh, yeah, 14. And we'll cons 1 on. Right? So building lists, building summations, no problem at all. Let's do some more. So I'm going to do another one. I'm just going to do this one. I'm not going to show you it first. We're going to find the length. Right? So if I want the length of a list, it's actually basically the same function as summation, isn't it? If you think about that for a second, you'll think it's true, I hope. So if we're at the end of the list, if list is empty, well, the length of an empty list is 0, isn't it? I can tell you that. Otherwise, so I'm going to do something. So I take a value off, so the head, but I don't need the head because I don't care what the values inside the list are. I only care that that value existed. So it's really just 1 plus the length of L.tail, right? And if we send that in to the interactive, we can say length of the empty list should be 0. Length of a list of 1 item should be 1. Length of 2 items should be 2. I forgot I have to put parenthesis around that. 3. I mean, we can just keep on going as we desire. So the length is not a difficult function. So it's very similar to summation because we're just adding for every element of the list, we're just adding an item. But instead of caring what's inside of the list, we just add 1 every time. Now, I'd like to point one thing out real quick. Notice that if you think about this as, I'm maybe this isn't helpful, I don't know. But if you were to think about this as a loop instead of recursion, what we're doing something for everything that's in the list, in the else, in the recursive case, and we have our stopping condition in the base case, right? So as long as we're not empty, we're just adding 1 every element through the list. As long as the list is not empty, we're just adding the head value, adding each value rather, through the list. It's helpful if you think about what you're doing for every element of a list in a recursive function of it. All right, let's write a function last, right? So this is going to be last element of a list. So if I want the last element of list, I actually want to stop 1 early, right? Because the last element, so like, I'm going to write this naive. I'm going to write the wrong version of this first. So if L is empty, then, well, what do I return? Well, I don't know, because I don't have anything to return, right? So I could return L, but that's just the empty list, right? So what I actually want is if L's tail is empty, that means we're 1 away from the last element, then I will return L.head because that's the last element there. All right. And otherwise, I just need to move towards that situation. So I don't really care about head, but I'm just going to do last L.tail until I get to that last element. Now, if you don't believe me, we'll just do this down here real quick. So down in the interactive, I'm going to do 1, : : 2, : : 3, : empty list, right? That gives me the list 1, 2, 3. If I do the tail of this list, right, I'm going to have 2, 3 empty list. If I do the tail of this list, I'm going to have 3 empty list. If I did the tail of this list, I would have the empty list, which means the head is the last element of the list. Right? I'm actually not sure what we're mad about here. Let's find out. It wants me to nail types down on it, so we'll just say L is a list. That might make it happy. Yeah, that made it happy. So here's our last function. Hey, oh, lowercase l, my bad. So here's our last function, and if I do last of the list 1, 2, 3, we should get 3 back. Hey, oh, list. Last of the list 1, 2, 3, we should get 3 back, right? If I did the last of, I don't know, 1, 2, I should get 2 out. If I do last of the empty list, what happens? We get a kaboom. Because we need another item. You probably didn't notice it, but we got a warning about this, I think. We probably got a warning about this. Oh, we didn't get a warning about it. You might get a warning about it in some situations that you haven't matched all the possible things that can happen, but it'll happen. Well, if I got last, could I get the nth item of a list? Right? So let recursive nth. Well, in order to get nth, we have to know what number we want and have a list. Well, if we want the nth item of the list, if for every recursive call we just subtract 1 from n, eventually n will equal to 1. And we can return the value that we have. Otherwise, we can just call nth, just like we were calling last. We'll subtract 1 from n, so that we're getting closer to the base case, and we'll pass in L.tail to coincide with that. We're always getting closer and closer to n equal 1. We're always taking an item off of the list, which means that we are getting the nth item of the list eventually. So that works. And we can say nth, let's get the second value of true, false, true, right? So we expect this to be, I think, false. Oop. Notice I used a comma on accident. Don't be like that. Use semicolons, right? So if I ask for the third item of this list, hopefully it's true. If I ask for the first item of the list, it will be the first true, right? So that's nth. All right. One thing that's useful when you're doing list operations, you may want to start at the identity function. So the identity function is just a function that takes the thing and it reconstructs it and it returns the same thing, right? So the identity function here, we have a recursive function that's going to take a list and it's going to build a new list. So that's what we're doing here with cons. But we're going to build that new list one element at a time. So then the identity function, if we have an empty list, then we return an empty list. Otherwise, we put the head onto the identity of the tail. So we're consing the head onto the tail of the same list, right? We're rebuilding the tail to be the tail again. So the identity of the list 1, 2, 3 is the list 1, 2, 3. This is useful because oftentimes when you want to do something to each element of a list, if you start with this identity function and just modify it a little bit, you'll get the new thing you want to do. So if we wanted to double every element of a list, for instance, right? Let's write the identity function real quick, and then we'll write the double function. So let rec identity of a list. If the list is empty, then we'll return empty. Otherwise, we'll return l.head consed onto the identity of l.tail. Right? That's the identity function right there. And we can try it out. I always recommend trying these kinds of things out so you see the result. Come on, indentation options, you can do it. Come on, indentation options, there we go. All right. So the identity of the list 1, 2, 3 is the list 1, 2, 3, no problem, right? Now, what if I want to write the double function? Well, I'm going to take my identity function and I'm going to duplicate it. I'm going to call this dbl for double. I want to double every l.head. Well, I'll just multiply them by 2. I'll change this to be an int list. And I'll change the recursive call to be a call to double. Now, I am multiplying every element of this list by 2. So when I call double of 1, 2, 3, I expect to get 2, 4, 6 out. And it's that easy. That's how you get good at this kind of stuff. You have to notice patterns and then say, oh, hey, I can apply that pattern to this problem that I'm trying to solve. All right? All right. I'm going to tell you that you need to do exactly this stuff. I want you guys to have practice with this stuff, and I'm just kind of doing these in front of you. I want you guys to write these other functions in your own F# interpreters and take the time to do exercise 6 in these slides. Now, in a normal semester, I might give you a quiz over this. I'm not going to do that today, but I want you to go through here and type these in and do exercise 6 on your own so you get the practice doing function writing and seeing the results in an F# interactive like this, right? There are a bunch of them here, and some of these have hints and some of these have answers. Don't look at the answers before you write the function, otherwise you're not learning anything. But exercise 6 is a good way for you to get used to writing these kinds of functions. All right? And I'm doing this because my voice is giving out, just so you know. All right. So at the end of all this, what do we have? We have F# types. Right now we have int, float, bool, character, and string. We have tuples and lists and functions. Those are all the types we know about right now, and honestly, they're about enough for us, right? We don't really need a lot more than this for what we're going to do. There are other types out there. Every type that the .NET CLR knows, so every type that's available to you in a language like C# or managed C++ or any number of those other .NET languages, they're all available. But these are the only ones that we're really going to need. Now, the next thing that we do is going to be making all of this recursion a lot easier and making it so that we can get various elements out of lists and that kind of stuff. So stay tuned, we will do that on Thursday. Until then, you have enough information to do homework 1. Right? I'm gonna go click through to it real quick. So if you didn't get writer and all that stuff working, pay attention at the beginning of today's video. I made some notes about how to run the unit tests. You have enough information to do homework 1. I have some information in here that is actually the same. If you're going to run .NET 5, you actually probably want to do this stuff. Don't worry about this section. I meant to take that out and didn't. But you have enough information to do all this. There is one thing I want to note here. In number 2, we have this funny stuff about factorial. Factorial of 20 is bigger than an integer, and so we need something. We need a big integer to get that. I want you to notice that if I just say big int and an integer, it converts that integer to big integer, right? So you can always get a big integer out of an integer. So what you need to do, you need to write a factorial function. We have plenty of examples of factorial functions in the notes, that instead of an integer, returns us a big integer. Now, you don't have to take a big integer to return a big integer. You just have to make sure each of the return values is a big integer, right? I want to show you a couple of things in the IDE real quick about that. So if I say big int 3, that converts 3 to a big int. I can multiply big ints together. So big int 3 times big int 4 is big int 12. All right. Let's write double so that it returns us a big int list, right? So this is going to return us a big int list. And in order to do that, so this return value has to be a big int list, which it is because it's an empty list and we can put anything in it. But in order to do that, we have to change this return type to be a big int list. And notice here it's got an underline on 2. And that's because l.head is an integer, right, times 2, and this whole thing has to be a big int to create a big int list. So we need to explicitly convert l.head to a big int. Oops. And we need to explicitly convert 2 to a big int to get a big int list out of it. Now double takes an int list and returns us a big int list. So dbl, the list 1, 2, 3 now is going to be big int to big int for big int 6. And it looks ugly, but hey, it's there. So you see 2 here, we have 4 here, and we have 6 here. So this technique right here, you're going to have to do the same thing to the factorial function. All right? I just want to make that note because that is a thing that confuses people. When you do that, when you take the factorial of 20, you're not going to get a negative int out. You're going to get a big int that actually is factorial 20. And you must do that, because if you don't do that, then C of 20 and 5 is not going to equal 15504. It's going to equal something else, right? I think the rest of these are actually pretty straightforward. MatAdd is actually a very simple function. You're going to use vecadd. You're going to write basically vecadd over, except for instead of taking lists, you're going to take lists of lists to multiply, and you're going to use vecadd instead of add, right? All right. I think that's all I have to say about that right now. If you have other questions, feel free to ask in Discord. Otherwise, I'm going to let you go and drink some hot tea and hope that I'm got a voice in whatever, an hour and 45 minutes. So have a nice evening. I'll catch you guys on Thursday at 10.